Hi, welcome to the SPDK Virtual Forum 2022. My name's Jim Harris. I'm a principal software engineer at Intel, also one of the SPDK core maintainers. I'm going to kick off the virtual forum with a talk on the state of the project. So as in past forums, I'm going to break this up into three parts. We'll start off with an update on the community, what's been going on with the project from a community level, and then we'll dig into more of the technology. First, looking back over the last 12 months and giving an update on what's been added to the project, and then also looking forward on what we can expect over this next year. Okay, so milestones over the last 12 months. One of the changes that we made as a project was moving from a every 3 month or every quarterly cadence to doing one every 4 months. This was mainly to just kind of reduce the burden of the whole release process on the project as a whole. It also aligns with other projects that we're closely aligned to, like DPDK, which recently moved to a similar cadence. So over this last year, we did have 3 releases. We're going to still keep January as our cadence for the LTS. So we'll have another LTS release this coming January. And then we just most recently had our 22.09 release back in September. But we're marching quickly towards that next release in January, 23.01. We also added a new core maintainer to our ranks. So Konrad Steiber from Intel, he's based in Gdansk, Poland. Konrad has a long history of contributions across a lot of areas of SPDK. He's been the primary designer and developer of the storage management agent, which you're going to hear a lot about both in my talk and his talk and another talk later today. NVMe TCP, he's done a lot of work there on both the initiator and the target side. He's made a bunch of improvements to the tracing framework, the Intel VMD driver he developed. There's just a ton of stuff that he's done. He's also really a great code reviewer, a lot of attention to detail. He's a very welcome member to the core maintainer team. We also had our first SPDK community hackathon. Wish we could have done this in person, but the stars didn't align. But we had a great a several-hour session a few months ago where we focused primarily on the NVMe VFO user target. So for those that aren't familiar, you're going to hear more about this from John and Thanos from Nutanix later today. But this is where you have an SPDK VFO user application that is serving storage to virtual machines, and in the virtual machines they look like NVMe devices. And so this hackathon focused mostly on the target from a security perspective, so did a lot of code reviews, looked at things that we can do from a fuzzing perspective to continue to fuzz the target and look for security holes. And we're going to be continuing that work and hope to have more of these hackathons over this next year. And then also added performance regression tests. So Karl Letetsky, who is the primary author on all of our per-release performance reports, added nightly regression testing, which you can see out at performance.spdk.io. He's going to talk a lot more about this in a talk tomorrow. But this really kind of fills a gap that we had where we would do some ad hoc performance testing during the release cycle, but most of the results were collected after the release had already been tagged. And so now we have a number of key test cases that are tested on a every single night, basically pulling master, running the tests on some pretty tricked out hardware. And we can get that feedback quicker. And this has found some cases where there's been some, unintentional performance regressions, things that the functional testing didn't catch, but the performance regression testing now finds. Okay, so next, looking at the code. So we like to kind of look back on basically a release window. So year by year, how have things trended over time? And one of the biggest things that we saw over this last year, which I'm really excited about, is that we had 124 contributors over the last 11 months. It's actually a little bit less than a year, from 35 different companies. And those are both records for the project. It's really neat to see so many people just contributing to SPDK, finding areas they can contribute, just seeing people, working together to improve and fix and just make the project better overall. We've seen the number of commits go down a little bit. I'm not particularly concerned about this. There's still a lot of work going into the project. I think, some of this can just be a factor of the project, continuing to mature. And, maybe cases where we had a lot of commits to make some, small fixes here and there before. We don't see as many of those now. But I think one of the other interesting trends that I think is really good is that we're seeing, continuing to see a lower percentage of the overall commits come from the top 10 contributors to the project. So, we're seeing a lot more of the commits coming from a broader range of people. So, you still are going to have a lot of people who maybe just do 1 or 2 patches a quarter, but we have a lot of people that are just more regular contributors to the project. And so I think this is great, and it just improves the overall quality of the project with just a lot more people with their hands in the code. We also traditionally have liked to look at GitHub. What does the traffic, look like to the GitHub SPDK project? We continue to see that increase. We've seen that go up about 15% year over year. Okay, so now on the technology. So first, the storage management agent. You're going to hear there's a couple of talks coming on this later today that are going to touch on this. One will be from Yadong Li and Jarek Kogut, another one from Tomek Zavadsky and Konrad Steiber. They will both talk about the SMA, storage management agent, not just SMA, but about IPUs and how SPDK fits in general. So if you've got more questions about this, please check into those talks. But basically, SMA fills this gap for simplifying IPU orchestration. So when we look at SPDK applications that are running on like an IPU or a DPU, there's a fairly complex JSON RPC interface to get all that configured. There's a lot of steps involved. And so what we wanted to do was try to abstract some of those details from orchestration drivers so that the orchestration drivers can be more generic. They can focus more on high-level operations and not have to be down in the details on how do I send a whole sequence of JSON RPCs, and even worse, how might those RPCs differ between different types of IPUs or DPUs. And so this is what SMA really fits, is basically putting a lot of that complexity in the platform specifics and those sequence of operations into SMA and let the orchestration drivers basically operate at a higher level. So there's support on the front end. This is basically what gets presented up to the host for both NVMe and VirtIO block, and then allows to connect to remote NVMe storage on the back end. And so certainly if you want to hear more about this, check out those other talks later today. So next is NVMe Multipath. This work has been going on for a while. NVMe Multipath is not an easy it's not an easy feature to add. Thankfully, we've had Shuhei Matsumoto from NVIDIA who's been driving this work over the last year, and he's going to be talking more about this in a joint talk he's doing with Mike Gertz tomorrow. But basically, we have 2 multipath modes in SPDK today. These are implemented up in the BDEV NVMe module. So it's not in the NVMe driver itself, it's up at the BDEV NVMe module. First, we have what we call actual multipath mode, and this is based on NVMe ANA, asynchronous namespace access, where you use NVMe discovery to basically identify what are the paths to my storage, and then use ANA log pages to get information about which path is optimal. Then we also have what we call a failover mode, which is more manual, where the administrator can configure these paths manually, and then if one path fails, it'll switch over to the next one. We've also added a discovery service into the BDEV NVMe module itself, so you can point the BDEV NVMe module at a discovery service NQN, and then it will issue discovery log pages to that, identify the paths, connect to those paths, and basically enable that multipath mode automatically. So next, XNVMe. So XNVMe is an open source project. The primary author and developer, Simon Lund from Samsung, is going to be doing a talk on this tomorrow. And XNVMe is all about providing a common interface for all of the different interfaces to be able to access NVMe storage. So, for example, Linux AIO, IOU ring through the block layer. More recently, IOU ring command, which allows you to use IOU ring, but to tunnel directly to the NVMe driver to get the lowest overhead possible and the highest ability of configuration of those IOs. And so Simon's going to be talking about the Linux storage interfaces overall. He's going to be talking about how XNVMe enables those. And then he's also going to be talking about how this has been integrated with SPDK. So we now have a BDEV XNVMe module. And I think from an SPDK project perspective, I'm the most excited about this because I think this IOU ring command interface is the closest we've seen so far to the Linux kernel providing SPDK-like performance and efficiency capabilities. So it's probably never going to get all the way there from an efficiency perspective. Simon's going to talk a little bit about more about that tomorrow, but it provides a really interesting alternative to be able to still use the Linux kernel driver with an interface that gets maybe close to what the native SPDK user space driver gets from an efficiency perspective. And I think there's cases where this is needed, where maybe a user space driver is not a possibility, and so Linux and XNVMe is going to provide an alternative there. So next, the Accel Framework. There's been a lot of changes over the last year and are going to continue over the next year. I think one of the biggest things here that Paul Luce has been driving a lot of this is making the Accel Framework the primary interface for SPDK acceleration. So in the past, and we still have some of this today, we have the Accel Framework for doing things like copy offload and CRC offload. We use DPDK CryptoDev and CompressDev directly through a couple of BDEV modules to do crypto and compression offload. But what we want to do is we just want to pull all of that under the Accel Framework and have Accel Framework be the primary way to do that. So there's actually going to be 3 talks today and tomorrow about this. Later today, you're going to hear John Kariuki talk about how we use the Accel Framework and the Intel DSA engine to accelerate NVMe TCP data digests. Alexei Marchuk tomorrow is going to talk more about the work that he's been doing around Accel Framework for crypto and NVIDIA devices for doing that. And then Paul Luce is also going to be doing a talk just more generally around the Accel Framework, and all the work that's been going on is going to be happening over the next year. So briefly, some of the improvements we've had. IDXD is the driver for the Intel DSA engine on Sapphire Rapids. There's been a lot of work there to improve not just the driver, but also how the Accel Framework utilizes it. A lot of work around how do we configure all these different Accel modules. So the whole idea here is that the Accel Framework uses software as sort of a backup, but if there's hardware capabilities available, it's going to use that too. But we want to be able to enumerate what capabilities are on the system, even be able to select, like, I want to use hardware versus software for individual opcodes. Maybe from a functional perspective, but a lot of times from a testing perspective, you want to be able to do that. So for comparisons, being able to just make that very easy to be able to configure. So we've already started pulling compression under the Accel Framework. Paul's done a bunch of work here to be able to use ISA-L as the software backend for compression, and the DPDK stuff is going to be quickly following. And then also vectored CRC32. So, we still see CRC is a really nice use case for the Accel Framework. In a lot of cases, we are doing CRC on very large IOs, but it's not just one buffer, it's vectored buffers. So we've got a bunch of 4 or 8K buffers, and for CRC it needs to be calculated serially across the whole buffer. And so Ben did some work with Greg Tucker from the IceL project and identified how we can calculate the CRCs for those individual buffers in parallel, and then use CRC math to be able to combine all those at the end to get a final result. And so we get much better throughput and efficiency by doing the CRCs on these large IOs in that way. Okay, so next, host FTL, so host flash translation layer. So there was a flash translation layer that was upstreamed into SPDK a few years ago, but it had a number of limitations, and most recently, a group at Intel has pushed a new version of this FTL up. Mateusz Kozlowski is going to be giving a talk on this. I think it's actually next after this talk, where he's going to talk about this work in a lot more detail. But the idea here is that we leverage, effectively 2 different types of storage to get better performance and efficiency to provide, best of class storage performance to an application. And so it kind of consists of 3 parts. So first, we have a persistent write buffer, which is basically aggregating writes that are coming in to an optimal write size. So we know we have some backing storage, and we want to aggregate a lot of writes that are coming in, because you can't do small 4K writes to NAND. You're going to get really bad performance. So we want to aggregate them all in a storage class that best handles that type of I/O pattern. And then we have a logical to physical map and metadata. So this is sort of like a global index and mapping table. This is persistent and byte addressable. The persistence and byte addressability can be handled a couple different ways. Currently, it's storing to an Optane SSD, but then caching portions of it in DRAM. But there's other ways that you could do that too, but that's sort of the second step. And then the final step is basically writing data to a cost-optimized backend NAND tier. So we have something called RAID 5F here. So Artur from the same team has developed something here. It's RAID 5, but the F stands for full. It's for full stripe writes. And so FTL can work with any BDEV on the back end, so it doesn't have to use this RAID. But the RAID is nice because effectively what we do is we can write a full stripe of data. But since we're always writing full stripes, we can read smaller portions, but the writes are always full stripes at a time. We avoid the performance penalty of in-place updates. We avoid the RAID write hole. So there's a lot more that goes to this. Please check out Mateusz's talk to hear more about it. And of course, there's a lot more. These are the heavy hitters. Some of the other ones, NVMe VFIO user optimizations. So John Levin and Thanos Makatos from Nutanix are going to be talking more about this. They're going to do a shorter talk to talk about what's been going on there. We had Dennis from Croy push a BDEV module for DAOS. So sort of kind of full circle. The DAOS project has used SPDK storage for a long time, and now SPDK can actually connect to DAOS for storage as well. So that's sort of an interesting turn of events. Talked a little bit about the IDXD driver. So doing transparent batching. Before we had a more explicit batching interface, so more recently we've made this more transparent. It matches more what we do in things like the NVMe PCIe driver, where we transparently batch doorbell writes so that you don't incur the costs of that. And so this is just a much more friendly interface to the IDXD user. A few other things, the ability to grow a blob store. So offline, if the underlying blob store device grows, you can actually grow the blob store sitting on top of it to take advantage of that new space. So VFIO user, we've been using it for NVMe, but it's can generically emulate any PCI device. And so Chongpong Liu added support for being able to do VirtIO block and SCSI over VFIO user. And so that's just it's a really interesting use case. We've already supported that through vhost before, but potentially down the road, VFIO user may be SPDK's primary way of doing this type of virtualization for NVMe and the VirtIO interfaces. And then also just general improvements to our tracing infrastructure. So I'm going to give a talk tomorrow to talk about this in more detail, but there's a number of improvements here. Okay, so looking forward. So I think orchestration is going to be one of the big areas of focus for the project moving forward. So for those that aren't familiar, there's under the Linux Foundation, the Open Programmable Infrastructure OPI project. And we've been pretty involved in there. Ben Walker, Conrad Steiber, myself, and others collaborating with OPI on what does storage orchestration look like. And so SPDK plays a big part in this, but not all IPUs and DPUs are based on SPDK. So we want to continue to collaborate with OPI and the vendors that are involved there to really drive these industry standard interfaces for IPUs and DPUs. And as part of that, we're going to continue to leverage SPDK and SMA. I think we'll see changes we need to, possibly make to SMA as we drive this forward. But I think this is going to be a key collaboration between SPDK and the OPI projects. More on the Accel framework. So, a lot of the stuff we talked about, crypto and compression, Alexi, Paul, and others are going to continue to be driving this forward to make this the central interface for SPDK. Wherever in SPDK we want to do crypto or compression, whether it's at a NVMe layer, whether it's down at the at the BDEV layer, like we have just a single Accel framework interface that we can talk to. So chaining, Paul's going to talk more about this, but we want to have the ability to chain individual Accel framework operations. And sometimes this can be complicated because sometimes you want to do a DMA and you want to do a decompress operation, but there are different parts of the SPDK stack. So what can we do in SPDK to be able to enable those types of complex acceleration use cases? So more hardware support. So talked about Quick Assist, NVIDIA, NICs. How do we add more support for that, and then more NVMe integration. So how do we actually take advantage of this in other parts of the NVMe, TCP, and RDMA stacks? So another one that I think is really interesting is container storage. So this is something that's come up a lot where we have the case where we want to serve SPDK storage, but not to a VM or to a remote node, but we want to serve it to local processes or containers on the same node. And so, looking back, originally way back when we used the Linux NBD interface, for this, but this just is not performant. This works well for maybe some very niche, more like management type, use cases where you want to be able to access that storage, but it's not designed from a performance perspective. So more recently, what we've seen a lot of people do with SPDK is NVMe over TCP loopback, and this is really the best option as of like this moment today. And so the idea here is that you start the SPDK target app up. You serve storage over NVMe over a TCP loopback interface. And then on the container side, it can use the kernel drivers to connect to the target and be able to access storage that way. But most recently, Red Hat has pushed something called UBLK, uBlock. It was pushed up in Linux 6.0. And this is really a native solution for this specific use case. So this is all block MQs, so we can do multi-queues. It's based on IOU rings, which is really the latest and greatest for an application like SPDK to communicate with the back end of a Linux kernel interface. And so Xiaodong Liu from the community is actively working on this. He has a POC that's working, but we're moving towards getting this really natively supported for the upcoming January release. And so this is really exciting. We think this is going to make it even more performant to be able to serve SPDK storage to these local processes and containers. And of course, there's going to be a lot more. blob store external snapshot. So being able to have a clone in SPDK blob store, but have the backend not be, have the snapshot not be another snapshot on the same blob store, but have it actually be another BDEV. Maybe it's a BDEV locally, maybe it's even remote. And Mike Gertz has been driving this, and he's going to talk about this in the co-presentation with Shuhei tomorrow. So a few others. We have some of this RAID support today, but it's all configured out of band. So adding on-disk metadata, we think this is going to become, well, there's been requests for this, but we're seeing more and more of it, and we have some people that are starting to work on this. More fuzzing, so looking at how do we extend our NVMe and our VirtIO fuzzers to fuzz more interesting data paths. More NVMe TCP optimizations. Ben's going to be talking, Ben Walker, later today about how do you do TCP for storage workloads. And so we continue to see new ways to be able to make optimizations there. We see new ways that the Linux kernel through IOU ring is enabling applications to be more efficient. So I think there's going to be a lot more work there as well. Hot upgrade infrastructure. So there's a lot of cases now where you want to, upgrade an SPDK application in place with no or very minimal loss of service. And so I think there's going to be quite a bit of work here that's going to be needed. I think this is going to be an active area of development over these next 12 months. And then finally, as we talk about security, we've been focusing more time on OpenSSF and some of the sort of the BKMs for really having more of a security mindset for open source projects, and I think we're doing well. We have more work to do, but I think there's going to be more focus on this over these next 12 months. One of the really interesting things that we learned recently is that as part of this, Google has defined a metric for criticality, which basically just means looking at a project, who's contributing, how long have they been contributing, what's the activity on the project, and just trying to have some level of measurement of like which projects out there are most critical to the open source ecosystem as a whole. And they actually run data on a regular basis across 100,000 GitHub projects, and we found SPDK was actually number 346 out of all those 100,000 projects. So I think this just really speaks to the activity of the project. The number of people that we have involved, the activity as far as like filing issues and responses on issues, and just really kind of moving things forward. It's really interesting to sort of see SPDK being recognized as a really critical project in the open source ecosystem. So that'll conclude my talk. Thank you for listening. Hope you enjoy the next couple days and learn a lot from these other talks, and hope to talk to you soon. Thanks.